We continue with the cluster analysis of the laterin and subbilateral. We don't need to go to this one. I just show you one result the program can generate here. The program can generate this one, the graph, and this graph we got heat map. Heat map. And look at here. Let's read the gene similar expression. Here, how many genes? 562 bacterial genes measured in 10 different experiments. Experiment from 1 to 10. 1 to 10. And then group into different clusters. First of all, cluster 13, 18 genes. 18 genes, that means 1 to 18. Okay? Along this column, that's a gene, And the genes, I read in the first 3 experiments, the red color, but then subsequent I read the green color. So based on the color, we will know gene expression similar between gene plots and compare between experiments. First of all, you can control between the disease sample, higher expression, so that's why red color, and then for the controls, lower expression, green color. That's how to group gene expression with the similar pattern into cluster and generate this one heat map. You also don't need to do anything, the program do for you. You just input the data in the program you do. That's the DNA microarrays. And why I need to explain DNA microarrays in detail? Because when we move to RNA sequencing approach, the principle to analyze data is similar. So that's why you need to understand the data analysis in microarray first. And after that, we move to RNA sequencing approach. And we compare which approach are more useful. And we can apply an sequencing approach because now we have NGS available. Before we cannot do it. Before, if you want to study many genes at the same time, you have to use microarrays. And microarrays actually expensive. And you need to know you need to know what. For the microarrays, you need to know gene sequence. Otherwise, you cannot design microarrays. And then now we move to an sequencing approach to see any more advantage compared with microarrays. RNA sequencing used to accomplish the same goals as microarrays. The same way, study gene expression, which gene expression and how much gene expression. Quantify RNA transcript levels. Consider revolutionary because, so that means compare between two approaches, RNA sequencing and microarrays. Allow measurement of essentially all RNA transcript. So, in this case, you don't need to know gene sequence in advance. You don't need to know that. Okay? So that's why study on RNA transcript. On RNA transcript, that means on gene expressed into the RNA. You don't need to know the gene sequence to design from. You don't need to know anything. A broader dynamic range doesn't matter the gene expressed very high level or low level, because sometimes the gene expressed at low levels you cannot attract enough for microarrays. You need less amount of RNA and revert into the cDNA. But in case you don't need large amount of RNA. Doesn't matter gene expressed at high or low level, we can apply RNA sequencing to sequence node. Another one allow identification of novel transcript and transcript isoform. Novel transcript, that means gene not yet studied before. Novel transcript, probably new gene. Maybe new gene we don't know before. Because sequencing technology is super more, okay, and can identify new gene we not yet studied before. Novel transcript and transcript isoform. So look at here how we draw transcript isoform. Already explained one genes and genes transcribed into primary transcript first still contain introns. Okay, and then splicing events happen to remove introns, and after that, different combination of exons. Okay, generates different mRNA, and different mRNA come from the same gene. We call families of mRNA synthesized into the protein. We call isoform. Okay, transcript isoform. If they come from the same, In sequencing approach can identify isoform. Compared with MiroBrace. If MiroBrace design crop and crops come from exon 1, and exon 1 can hybridize with any isoform here, and MiroBrace cannot distinguish the isoform. It is able to quantify alternative splicing event. So that means splicing generate more isoform 1 or more the other isoform. The sequencing can detect the splicing events. Which one more common? Generates which isoform common. Sequencing technology can do it. So that's why consider evolutionary technique, the RNA sequencing revolutionary technique due to some advantages here. We look at the flowchart of RNA sequencing, a simple flowchart. I also revised the DOI, and then you can access to this article because I copied on the article. Start with the RNA extractions, isolate mRNA, reverse into the CNAs, and then transcript fragmentations that prepare library for sequencing. And when you have the sequencing results, you have to process the data, and then de novos. You already know up to de novo assembly, and today you continue with the rich quantification, and after that, differential gene expressions or biological insights. So now, today we already finished up to de novo assembly. Now we study rich quantification, and why we need to do it? Because we need to quantify how many rich and integrate into differential gene expression. That's the one we study today. And then you see, because we base on sequencing approach, and we identify gene, for example, gene 1 express very high in the disease sample compared with the control. That true or not? Cannot confirm. How to confirm it? You have to go to validation. Validation using qPCR. qPCR, that means the technique to amplify RNA and then also can quantify how much RNA. So that the consider and the golden technique to measure gene expression. But in technique, you have to perform one by one gene. You cannot perform all genes at the same time. Okay? But here, the RNA sequencing approach identify which gene express differently between sample, and you may identify the key gene to validate. This gives the idea how to go further. Okay? Because that will go into the cancer, something like that. So that means you identify the key gene to go further with validation. You cannot do all. You cannot do all. The validation aspect very important. So go on process. You nearly go to the on process because we don't go to validation. If you set up experiment later, you need to go to this one. Nobody application requires validation, not stop at sequencing and analyze the result from sequencing. Then overviews of mRNA sequencing flowchart. Look at sequencing, reverse transcription, reference DNA. So on stack here, just cherry red. Okay, cherry red. And then data analysis. The raw rate quality check and processing on way do that. Now, mapping, counting. After counting, differential analysis and biological interpretation. Let me identify which genes express higher or lower. Differential analysis based on the counting and how to count based on mapping. So mapping, counting to step in rate quantification. Mapping. Because we study with RNA, so that means some consideration you need to know. RNA quality very important to obtain reliable, reproducible RNA sequence data. Because you sequence the data, you generate data that depends on the material, and the material here RNA quality good enough or not for sequencing. And how we know good enough or not? We base on this score, RNA integrity score, ring values, and ring value from 1 to 10. And how we know it? We use this machine, a Genomic bioanalyzer. Nowadays, this one. We also have other machine, but I say this machine is very common in many labs, a Genomic bioanalyzer. You know, the ring values less than 6. That is thing that's on the sequence sequencing and thus accept this ring. That means the quality, RNA quality, good enough for sequencing. If more than This one, how we do? If smaller than 6, how we do? If smaller than 6, how we do? Because this one, just the first step, checking at a quality only, not yet syncing, not yet syncing. If smaller than 6, what we do? Throw it away, isolate, and again. In case you don't have other sample, no choice. No choice. No choice. If no choice, we have to accept it and we take risk. Whether generate with sequence and generate high quality or not. And you already know how to check rate when we receive the data. Okay, and that's my case. Because I don't have the other sample, and I send sample to community space, specialized for sequencing in Singapore, Novogene. Novogene is not the community's specialized in sequencing, and they check on a quality first. And I send sample to them, and the report only 4. The ring value only 4, and conclusion fail. And also they recommend whether you want to sequence or not. If you want, that means you have risk. It's up to you. And I accept it because no choice, no more sample, but actually later the risk quality also very high. Okay, and then here, acceptable standards not always the same for the organism you study. Because I study shrimp sample and maybe shrimp sample different with the other organism. Very hard to isolate high on a quality. Maybe contaminate with the other ones, but not affect to sequencing, not affect to sequencing. So that's why sometimes we need to take risk. Otherwise, no data. Okay, normally sick, very good, but it depends on what I mean here. Depends on organism you study. Okay, not always rely on this value. Not always rely on this value. Okay, stop here 15 minutes.